Welcome to the Insightful Professor. In this current video, we continue our examination of normalization theory. We will investigate two advanced normal forms, Boyce-Codd Normal Form, abbreviated BCNF, and fourth normal form. As we noted in our previous video, transforming an entity relationship model into a set of relations or tables typically results in well-structured relations. However, there's no guarantee that all anomalies will be removed during that transformation process. We indicated that normalization is a formal process by which we can decide which attributes should be grouped together in a relation to avoid anomalies. What we mean by well-structured relations would be a relation or table that is devoid of anomalies. That's the motivation in our presentation of normalization theory. The objectives of this current presentation include introducing the advanced normal forms of Boyce-Codd Normal Form and fourth normal form. We will review the concept of functional dependency, which was introduced in the earlier video, and use that to discuss a concept of determinant. We'll talk about the anomalies that motivate the need for Boyce-Codd Normal Form. We'll introduce the concept of multivalued dependency, and this will lead us into a definition of fourth normal form. And as we do this, we'll discuss some of the anomalies that motivate the need for a higher normal form, such as fourth normal form. Along the way, we'll demonstrate how normalization is used to decompose a relation with anomalies into relations that eliminate the anomalies. Recall that a normal form is a state of a relation that requires that certain rules regarding relationships between attributes are satisfied. A relation that is in a higher normal form is closer to achieving the status of being well-structured. With each transformation from a lower normal form to a higher normal form, we eliminate or at least reduce the likelihood of an anomaly through data manipulation. Although the highest normal form generally is considered to be fifth normal form, we comment that this is a theoretical ideal. It's difficult to produce a practical example of a table which is in fourth normal form, but not in fifth normal form. So in practice, tables are often reduced to simply third normal form or Boyce-Codd normal form. In our earlier video, we introduced the concept of functional dependence. At that time, we noted that functional dependence was the basis for Codd's first normal form, second normal form, and third normal form. Assuming the existence of a relation R, some attribute y of R is said to be functionally dependent on another attribute x, also of R, if and only if each value of x has associated with it precisely one value of y at any point in time. Our notation here says relation R dot x, that is attribute x of R, functionally determines attribute y of relation R. And again, this can be expressed concisely and informally as, if you tell me the value of x, I can tell you the value of y. The definition of third normal form, as presented by Codd, had some problems. It did not adequately address a relation that had certain conditions. These conditions were, there were multiple candidate keys. The candidate keys were composite, and the candidate keys overlapped, meaning that they had at least one attribute in common. Although relations with these three conditions do not occur very often, the definition of third normal form fell short and allowed for anomalies to still occur. And this is where Boyce brought to Codd's attention and collaborated with Codd to come up with a new definition. Note that if these three conditions are not met by a relation, the definition of third normal form is satisfactory. In fact, both third normal form and Boyce-Codd normal form would then agree that the relation was well structured. To prepare for our definition of Boyce-Codd normal form, we introduce a new term, determinant. A determinant is any attribute on which some other attribute is functionally dependent. As we look at the employee number functionally determining employee name, employee number is a determinant. So using our notation with the arrow indicating functional determiner, what we see is that whatever appears to the left of the arrow is the determinant. So a relation R is said to be in Boyce-Codd normal form if and only if every determinant is a candidate key. The interesting observation we can make about this definition is that it makes no reference to any lower normal forms. Remember, Codd's definition of second normal form said a relation is in second normal form if it has no partial dependencies, plus it is in first normal form. A relation is in third normal form if there's no transitive dependencies, plus it's already in second normal form. So Codd was kind of building his definitions of higher normal forms on earlier normal forms. This is a perhaps cleaner type of definition. Although this provides a stronger definition than Codd's third normal form, and we'll see just how it compares to that in a moment, it didn't make sense to replace the original definition of Codd's third normal form with this definition. Here we present a relation that we name advisor. This relation happens to be in third normal form, but it is not in Boyce-Codd normal form. We'll use this to initially discuss the differences between third normal form and Boyce-Codd normal form. Here we see that a student identified using SID can have one or more majors. Notice that student ID 300 majors in psychology, student ID 300 majors in math. So a student ID can have one or more majors. Therefore, student ID, or SID, does not determine major, because major has multiple values. Remember the notion of functional dependency that says X functionally determines Y. We obtain a single value of Y by announcing the value of X. So here we announce the value of SID as 300, and we don't get a single major, we get potentially multiple majors. Therefore, SID does not determine major. Now, a major can have several faculty advisors. A faculty advisor is identified by F name. So here what we see is students could also have several advisors. Notice that in the case of student 300, once again, student 300 is advised by two different faculty members. This is because a faculty member advises in only one major area. So in the case of psychology, we see one faculty advisor for student 300, and in the case of math, it must be a different faculty advisor. So SID also does not determine faculty name. Therefore, SID cannot be a key. Here are some observations from what we've just determined. The combination of SID and major determine faculty name. The combination of SID and faculty name determine major. Therefore, either of these combinations can be a key. So we have two candidate keys. Remember, we have SID and major determining all of the remaining attributes, which happen to be faculty name, or SID and faculty name determining all of the remaining attributes, which happens to be only major. So therefore, each combination qualifies as a candidate key. But notice that faculty name is also a determinant because it determines major. Remember that a faculty member advises in only one major area. So we actually have 3 determinants in this table. Given our definition of third normal form, advisor satisfies the requirements of third normal form. But given the way in which we've defined Boyce-Codd normal form, advisor does not qualify as meeting Boyce-Codd normal form. We see the 3 conditions being satisfied here, where Boyce-Codd normal form enters into the picture. We have multiple candidate keys. These candidate keys are composite, and these candidate keys overlap. As a result, we have potential problems, potential anomalies. There's a deletion anomaly. Suppose that student 300 drops out of school. If we were to delete the row for student 300, we would also delete the fact that Pearls advises in psychology. Let's backtrack for a moment. Deleting student 300 would cause these bottom 2 rows to be removed. And notice in one of those rows, where student 300 has a major of psychology, that's the only row where we see the connection between Pearls being an advisor for psychology. Therefore, if we remove that row, we've removed another fact that Pearls advises in psychology. There's an insertion anomaly. How can we store the fact that Keynes, who's been hired, advises in economics? In order to insert a row in advisor, we have to have a valid primary key. If we consider SID and faculty name as a candidate key, then in order for Keynes to be inserted, Keynes must have a student ID, must have a student advisor. The solution is decomposition once again. We can take advisor and decompose it into 2 relations that have no anomaly. We can take advisor and decompose it into 2 relations with no anomalies. We would have student advisor, which contains student ID and faculty name. We can have advisor subject, which contains faculty name and subject. And again, this should be a non-loss decomposition. We'll consider a few other examples, in fact, several other examples, to give you a better feel for what Boyce-Codd normal form is, distinct from third normal form, and why third normal form is insufficient as was originally defined by Codd. We now look at several tables or relations and assess whether these tables are in third normal form or Boyce-Codd normal form, or both, or neither normal form. To pass judgment, we consider only the semantics of the functional dependencies of the attributes within the table. We do not explicitly present the application domain to avoid clouding our judgment. What we want to do is concentrate on the semantics of the functional dependencies together with our definitions of what constitutes third normal form and Boyce-Codd normal form. In this example, we have a table or relation named first, and we tell you that our assessment is it is not in third normal form, nor is it in Boyce-Codd normal form. The table or relation consists of the attributes of S number, status, city, P number, and quantity. We're told that the primary key has been designated as S number and P number. a composite primary key. The functional dependencies are given here, showing that the combination of S number and P number functionally determine status, city, quantity, S number, and P number, all of the attributes. This is what qualifies as the primary key. But we're also told that there are additional functional dependencies. S number by itself determines status. S number by itself determines city. Additionally, city determines status. What we see is because city is not part of the key and it determines status, which is also not part of the key, we have a non-key attribute that functionally determines another non-key attribute. This is a transitive dependency. This is the reason, or one reason, why the relation is not considered to be in third normal form. Boyce-Codd normal form is not satisfied because every determinant must be a candidate key, and you can see that we have several determinants here, and not all of them qualify as a candidate key. Additionally, as we look at this, we can come up with a little bit more criticism of this table or relation called first. It contains partial dependencies as well as the transitive dependency. Therefore, first is not even in second normal form. So there are three determinants: the combination of S number, P number, the single attribute of S number, the single attribute of city. Two of the determinants, S number and city, are not candidate keys, therefore first does not qualify as being in Boyce-Codd normal form. Let's consider another example. We reveal the assessment here as second does not qualify as being in third normal form, nor does it qualify as being in Boyce-Codd normal form. Second has three attributes: S number, city, and status, and we're told that the primary key consists solely of S number. The functional dependencies, the semantics behind this, indicate that S number determines status, S number determines city, city determines status. Again, there is a transitive dependency where city, a non-key attribute, determines status, another non-key attribute. Therefore, this table or relation does not qualify as being in third normal form. There are two determinants, S number and city. City is not a candidate key, therefore this table or relation is not in Boyce-Codd normal form. We now consider a relation, SP, that qualifies as being in both third normal form and Boyce-Codd normal form. The attributes of this relation are S number, P number, and quantity. Again, we are given the fact that the primary key has been specified as S number and P number. The functional dependencies show us that S number, P number as a combination determines quantity, determines S number, determines P number, and that satisfies the idea of being a candidate key and subsequently a primary key. There are no other functional dependencies. We note that there are no partial or transitive dependencies. Hence, by definition of third normal form, SP qualifies for third normal form. There is only one determinant, S number, P number. It is a candidate key. Hence, SP also satisfies the requirements for Boyce-Codd normal form. Let's consider another example. SC qualifies as both third normal form and Boyce-Codd normal form. SC consists of the attributes S number and city. The primary key is S number. There's a functional dependency where S number determines city. There are no partial dependencies, nor are there transitive dependencies, so by definition, SC satisfies third normal form. There is only one determinant, S number, and it is a candidate key, so again, by definition, SC satisfies Boyce-Codd normal form. A similar example here, but a change in the attribute name. CS again, qualifies both as third normal form and as Boyce-Codd normal form. The attributes in CS consist of city and status. The primary key is city. There's a single functional dependency where city determines status. So once again, there are no partial dependencies, nor are there transitive dependencies. We qualify as third normal form. There's a single determinant of city. It's a candidate key. We again qualify as Boyce-Codd normal form. Another example where both third normal form and Boyce-Codd normal form are satisfied. The relation or table named S. This consists of the attributes S number, S name, status, and city. The functional dependencies are S number determines the name, it also determines the status, it also determines the city. This qualifies as a candidate key because it determines all of the remaining attributes. Additionally, S name determines S number, it determines status, it determines city. It also determines all of the remaining attributes. It too serves as a candidate key. Remember the issue or concern about third normal form being insufficient. 3 points must exist. 1. Multiple candidate keys. We have multiple candidate keys. 2. The keys are composite. That does not apply here. Both of the keys are atomic. 3. The keys overlap. You can only have overlapping keys if you have composite keys, so also that does not apply. Therefore, there's no basis here to rule out Boyce-Codd normal form. So this particular relation or table does indeed satisfy both third normal form and Boyce-Codd normal form. One of the changes between this relation and the same attributes appearing in other relations in our examples was that city does not determine status. Consider again the definition of transitive dependency. S number determines S name, which determines city, is not a transitive dependency. We pose to you the question of why not? Remember that we only consider non-key attributes when looking for transitive dependency. S name is a candidate key, so it is not a non-key attribute. One final example regarding Boyce-Codd normal form is the table or relation SSP. This consists of the attributes of S number, S name, P number, and quantity. The functional dependencies are as shown here. S number determines S name. S name determines S number. And then we have composites. S number, P number as a combination determines quantity. S number, S name, and P number. S name and P number as a combination determine quantity, S number, S name, and P name. Hence, there are multiple composite candidate keys, S number and P number, S name and P number. We don't have the concept of a partial dependency as applies to second normal form, and again we ask why. The reason is S number by itself determines S name, but S name is not a non-key field. It is part of a key. The same is true for S name as a determinant. This is the reason that introducing the term determinant is so useful in clarifying functional dependencies and determining keys and qualification for a particular normal form. So SSP qualifies as being in third normal form. There are no partial dependencies, nor are there transitive dependencies. However, SSP does not qualify as being in Boyce-Codd normal form. S number and S name are not candidate keys, yet they are determinants, and every determinant must be a candidate key. The solution to bring this up to a level of being in Boyce-Codd normal form is to decompose the relation SSP into two relations. One which we'll call S, which consists of S number and S name, and the second, which we refer to here as SP, consisting of S number, P number, and quantity. Some final thoughts regarding relation SSP. Given that SSP consists of S number, S name, P number, and quantity, such that S number and S name are both unique, SSP then has two candidate keys. S number and P number could serve as a primary key. S name and P number could serve as a primary key. This is a case of overlapping candidate keys, since P number is present in both candidate keys. Finally, we reach the notion of what's called a multivalued dependency. When a relation is in Boyce-Codd normal form, there are no longer any anomalies that could result from functional dependencies. However, it is still possible that anomalies could result from something called a multivalued dependency. Consider a situation where a student is allowed to enroll in several majors. Student would be identified by SID, the majors identified by major. The relationship then between SID and major is not a functional dependency. The reason being SID, which serves as the determinant, is paired with more than one value, the value of each major for this student. A functional dependency is such that the determinant is paired with only one value of another attribute. This attribute dependency is referred to as a multivalued dependency, or MVD. The point here is that SID does not determine a single value, but rather it determines multiple values, or is said to multi-determine major. Let's go a step further and suppose that there is another multivalued dependency where student participates in several different activities. Additionally, majors and activities are completely independent of one another. What we have would be two one-to-many relationships captured within the same table. There's a relationship between student and major, so SID multi-determines major, and there's a second relationship between student and activity. Student ID multi-determines activity. But there is no association or relationship between major and activity. These are two independent objects or concepts. Thus, the two multivalued dependencies are depicted here using our notation for multi-determine. SID multi-determines major. Notice it's a double-headed arrow. SID multi-determines activity. In general, a multivalued dependency exists when there are at least three attributes in a relation, two of them are multivalued, and their values depend only on the third attribute. In a relation R consisting of attributes A, B, C, a multivalued dependency exists if A multi-determines values of B and A multi-determines values of C, and B and C are independent of one another. Let's examine the table shown here, and suppose that student 100, who appears in multiple rows, decides to sign up for skiing. At the moment, student 100 participates in swimming and participates in tennis. If we simply add a row that says SID is 100, music is the major of this student, and skiing is the activity, this would imply that the student skis as a consequence of being a music major. However, this student happens to major also in accounting. Therefore, in order to accurately record the fact that student 100 skis, and this activity of skiing is independent of whatever major or majors the student might have, it's necessary to add one row for each major paired with skiing. This is a type of update anomaly. Consider the consequences of having the table now represent student 100 with the multiple majors and the multiple activities. To remove the multi-valued dependency from a relation or table, we divide the relation into two new relations or tables. Each of these tables will contain two attributes that have a multi-valued relationship occurring in the original relation. Consider what happens if a student drops a major. Because a student can have multiple majors, we have to consider the implications there, but also because a student could have multiple activities. This also is related to this issue of the student dropping a major. To eliminate the anomalies that result from the table as we've described it, capturing the two multi-valued dependencies in a single table, we have to eliminate the multi-valued dependencies that exist. To eliminate these anomalies, it's necessary to eliminate the multi-valued dependencies. We build two relations, each one storing data for only one of the multi-valued attributes. Here we suggest student major, having SID and major, and student act, having SID and activity. This brings us to a summary of the point of what is called fourth normal form. Fourth normal form pertains to the notion of multi-valued dependencies and multi-valued attributes. A relation is said to be in fourth normal form if it is in Boyce-Codd normal form and has no multi-valued dependencies. Notice we resolve the problem through decomposition once again. The decomposition is done without loss. And we can verify this by reconstructing the original table by joining the two new tables or relations. We mentioned in passing that although there is a fifth normal form and a sixth normal form, they may be of limited use, highly specialized situations. They pertain to situations, again, that do not occur very often in practice. Therefore, we conclude our discussion of normalization theory, stopping here at fourth normal form. So in this video, we introduced advanced normal forms of Boyce-Codd normal form and fourth normal form. We reviewed the concept of functional dependency and then introduced the concept of a determinant. Furthermore, we introduced the concept of a multi-valued dependency, or an MVD. In so doing, we were able to discuss the anomalies that motivate the need for Boyce-Codd normal form, and furthermore, the need for fourth normal form. We demonstrated how normalization is used to decompose a relation with anomalies into relations that eliminate these anomalies. If you found this video informative, give us a thumbs up. Consider subscribing to the channel to show your support, and furthermore, you'll be notified when we post new videos. And finally, thanks for watching.